behavior of materials, and everything comes from the interaction between two opposing forces, whatever those two opposing forces are, right? Whatever those two opposing forces are. In this classroom, the two opposing forces are electrostatic charges, right? So this isn't, keep in mind, these aren't directions on a number line. That's not what these are, right? These are electrostatic forces. So you guys have walked over a carpet and shocked yourself by touching something metal, right? That zap was not a number line, right? That was not imaginary in your head. That was something physical that hurt, right? So these are actual forces that interact with the matter in the universe that create everything. These are forces, not directions on a number line. So if we, I know I'm going to get to bonding, I promise. I'm just a little sidetracked. You guys doing okay? Yeah? Cool. You having a good couple days back? Yeah? You missed your naps? Are likely to give up their electrons and which atoms are likely to take electrons. We know that. And if we think about atoms as oranges, obviously they were on sale. My husband bought a 30-pound bag of oranges. You're like, yeah, that's crazy count. I've been eating oranges. So if this is an atom and this is an atom, if they're far away from each other, they don't interact, right? And they're definitely not going to bond. So the only thing that gets them really to bond is they literally have to be physically close enough. Does that make sense to you guys? So when two atoms come physically close to each other, it's the outside that interacts, right? It's the outside of the atom that interacts. And do you guys remember what the electrons are called on the outside of atoms? Valence electrons, right? So those are the only ones like we're crazy concerned about, are the ones on the outside. Now remember, it's the outside of the whole, right? It's all the way, right? Oranges. Okay. So electrons, protons, these guys are in the nucleus. And they have their own job. They attract the electrons. There is that nuclear force that holds and pulls all the electrons to it. Surrounded by tons of electrons. We did the configurations, but from now on, we're just going to be concerned with the valence electrons. And let's do a super quick review. Looking at the periodic table, group 1A has how many valence electrons? 1. So everything in group A has 1 valence electrons. And in group 2A, there's 2. And I'm going to draw them like this, like a little pair. Now, the transition metals, they just kind of get skipped over because they're so different. Then we got 3A. How many valence electrons in 3A? 3. And you'll see them written like this. 1, 2, 3. So what I want you to think of is, here is the element symbol. Here is the element symbol, whatever the element symbol is, and here is the element symbol. 4A, otherwise known as the carbon family, has how many valence electrons? 4. 1, 2, 3, 4. And all the ones in group 4A, all the ones down. So under carbon is what? They're taped to your desk, guys. Your periodic tables are, right? And how many valence electrons in silicon? 4, right? So it's all the way down. Remember, this pattern goes all the way down for the groups. 5A, what do you think? 5. Now, watch how I put this in. It's called the clock method. I want to zoom in a little bit more. I shouldn't have made that so small for you guys. Sorry. It's called the clock method. It doesn't matter where you start, but you're doing 12, 3, 6, 9. So I need to put 5 in. 1, 2, 3, 4, 5. What this has done is it has shown me that I have 1 pair of electrons and 3 unpaired electrons in around the atom. Yes?
So for 4A, is it for unpaired electrons?
Yes. Excellent question. Excellent question. So for 6A, now again, it doesn't matter where you start. I'll start at 3 o'clock. 1, 2, 3, 4, 5, 6. And if I see that, I have 2 paired electrons and 2 unpaired electrons. What about 7A? What am I going to have? 3 pairs, 1 unpaired. Okay, excellent. So then 1, 2, 3, 4, 5, 6, 7. I recommend you get used to the clock method. It's going to help when we get into geometries next unit. If you do the clock method, you'll be left with the right angles. So it's not random where you put them around. It's not random. Try to put them around on the sides. But these represent the valence electrons. So these are the valence electrons by group on the periodic table, and they hold true all the way down. And we care about valence electrons because that is how atoms interact. That's the first thing that touch each other, are the valence electrons. And it is the valence electrons that are responsible for the bonding. So if we think about bonding, bonding occurs between 2 atoms, right? Bonding is between 2 atoms. So 2 atoms, between the 2 atoms, how are their valence electrons going to respond? Well, it really depends. They come up next to each other. They kind of sum each other up. It depends on the characters of the atoms themselves, the properties of the atoms themselves. One might go, hey, I'm bigger than you. One might go, hey, look, I got this little stub thing and you don't, you've lost yours, no stub thing, right? They literally have different properties. So it does ultimately depend on the properties of the atoms when they come together. Now you might be wondering, why do they bond in the first place? Bonding is between 2 atoms to become more stable. And there's all kinds of stability you might think of. We can think of it literally like potential energy. If you've got a hill and a valley and you're teetering on this hill, high potential energy, less stable. You roll down the hill, you end up here, lower energy of position, more stable, right? So atoms will bond to become more stable. And if you go on in sciences, you'll find out that that means energetically stable, which is the energy between it. Yes?
Can you go back to where you're showing the electron together? Why, how come 6 doesn't have a pair on the top?
Oh, I just started at 3 to show you that you can start anywhere. Yeah, you can start anywhere around the clock, but just once you start, it's 1 per each side in those positions.
Like there can't be like 2 pairs on opposite sides.
No, right. Yeah. And if you stick with the clock method, then you'll get your stuff right in the future. Yeah, 12, 3, 6, 9, and you can start anywhere. Good question. Okay, so they bond. Why do atoms bond? Yeah, to become more stable. We all want stability. We all want to become more stable. So then let's split it up by types of bonds because we know that's coming. Let's split it up by types of bonds. And then we'll split from those even more. So the first type of bond we're going to talk about are ionic bonds. Ionic bonds. It's the first type of bond. And it is between a metal and a non-metal. Metal and a non-metal. So that is, okay, they're going to get close. And when they get close, one's a metal and one's a non-metal. So they're going to behave a certain way. I'm going to form an ionic bond. I'm going to form an ionic bond. Well, what does that really mean? Well, as it turns out, non-metals are bullies. Straight up bullies. The non-metal is going to come right over to this and take an electron. And you're like, what? Come on, they're just atoms. They can't be bullies. What even makes an atom tough anyway? Right? So it's between a metal and a non-metal. And the non-metal forcibly removes electron from metal. So the non-metal removes an electron from the metal. So let's get back to how on earth does an atom become a bully? And I told you the non-metals are the bullies, right? So everyone has these taped to your tables so you can follow along. If we just highlight the non-metals here, you don't have to do it. You can just sit back and so yeah, noble gases are non-metals, but they don't really react, so we don't care about those. So we're looking at these guys here and hydrogen, right? And remember, hydrogen's really over here. Now, also remember a couple other things. Energy levels. This one has 1, this guy has 2, this guy has 3, this guy has 4, right? Everything in period 4. So we know the atomic radius for the size gets bigger as we go down, right? Size gets bigger as we go down. In the center is that strong positive nuclear force, that charge. And then out here are the electrons. Well, there's a distance between the nuclear force and the electron there, right? And there's a distance between the nuclear force and the electron there. And the distance between the nuclear force and the electron. And the distance gets greater between the nuclear force and the electron. Make sense to you guys? As you go down. Well, stay with me. I have a charge and I have another charge. And there is this force in between them. These two happen to be opposite charges, so there's an attractive force between them. Just some force. Make sense? Now, if I were to put them closer together, I'm literally going to move that charge closer. Now, this force between them is still an attractive force between them. Is it stronger? Yeah. Okay, stronger. Good. So, and then if I were to get them far apart, right? So there's still a force between them, but is it as strong?
No.
No. So we have distance between forces, right? And the further apart they are from each other, the weaker, and the closer they are, the stronger. But what if I have, let's say, a really big plus on this side? like a lot of nuclear force. Does that increase the force between here and here? Yeah, sure does. So distance between forces affects the strength of the force, but so does the actual size of the force. Size of force. So all of this kind of sums up everything you need to know. Now, it doesn't matter if they're the same forces, because even if you have the same charges, that force in between them is just repulsive, right? It's just pushing apart. And if I separate those positive charges to way out here, you have less of a repulsive force, right? And if I get them real close, you have a greater repulsive force, right? So, and then if they're opposites, it's an attractive force. So we have this force that's either pulling them together or pushing them apart, and it's going to change with distance and the actual size of the force. So we have distance and size. This whole relationship is summed up in something called Coulomb's law. Coulomb's law. Bless you.
Thank you.
And Coulomb's law is just a relationship, right? It's just saying that force is proportional, right? So let's give this particle a name. We'll call it particle 1, Q1. And this particle a name. We'll call that Q2. And they're right next to each other, meaning they're inversely related. When one goes up, the other one goes down, right? Just mathematically, they're being multiplied together. And that is based on the size of the force, right? This is twice as big, that's half as big, right? So that's just how it relates. So that's straight up just having two forces, either like this or like this. But then if we add distance to it, we're actually going to divide. It's directly proportional to distance. Direct mathematical relationship is divide. One is directly over top of the other one. And I know it's helpful to use D for distance, but since we're talking about atoms and subatomic particles, we're actually going to use radius, right? So R squared. So Coulomb's law basically is the mathematical representation of this. If one force is greater than the other force, that increases the force between them. If they're identical, you have force between them. But what is more important is the distance between the forces. And that's why it's squared, right? That's why it's squared. You literally cut the force by a factor of 4. If you double the distance between two particles, the force go down by 4. Not 2, 2 squared. 4. Right? So what does that have to do with these guys? Okay. As we go across, we're increasing the nuclear force. Fluorine has a whole bunch of protons, nuclear force. Whole bunch of nuclear force. How many protons does fluorine have?
9.
9. So we have 9 pluses, and it only has 2 energy levels. So we have a nuclear force, and if you remember, nuclear force is Z, so we have a value of 9Z in here. And our distance to our electrons, no matter how many there are, is fairly small, right? And distance between charges is more important. If we go down one, under fluorine is chlorine. So what's the value for chlorine? 17, right? So we have 17Z, but chlorine has 3, right? So the distance is further. Does that make sense? So the greatest charge, nuclear charge, Z to distance, is in fluorine. What does that mean? Just like in Stranger Things, the nuclear force can punch a hole through this little area of, uh, of orbitals, reach out and grab an electron from another atom and pull it in. Right? It's that strong. So when this happy little atom comes along, ooh, I'm a metal. This guy just like the other world, like the underworld thing. It just reaches out and takes that electron because it's that nuclear force is so close to the rest of the world, right? What I've just described to you is called electronegativity. 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 It comes from a strong nuclear force, so a strong Z, a lot of protons, right? A strong nuclear force, and a short distance to valence electrons. Short distance to valence electrons. That's where an atom gets its electronegativity. It is defined as an atom's ability to attract electrons in a bond. Now, on the first one of the worksheets you picked up, the one called Identified Bonding, there's a table at the bottom of it. Looks like this. There's a table at the bottom of it. It's a little different than the periodic table on your desk because it has these weird values, and it's actually called the Pauling scale. And these values are actual electrostatic Coulombic forces, Coulomb's law, right? And it ranks fluorine as the toughest of them all. It is the most electronegative. It has an electronegativity value of 4. It's the strongest guy out there. Now, this trend is diagonal. So the weakest guy out there is francium, right? Think about it. Francium, yeah, it has a lot of protons in the nucleus, but it has 7 orbitals, right? Those valence electrons are really far away from that nucleus, right? So distance is more important than charge, right? Distance is more important than charge. So that makes francium so little, and fluorine so great in electronegativity, an atom's ability to attract electrons in a bond. Now, you will notice if you look at the nonmetals, carbon, just kind of over here, we're at 2.1 is our lowest, and hydrogen is 2.1, right? Electronegativity values. Now, start checking out these metals. Less than 1, 1, 1, 1, 1, 5, 1, 6, 1, 5, 1, 8. Nowhere near 2, right? And really not near 4. Ionic bonds. Stay with me. Ionic bonds. Between metal and nonmetal. The nonmetal removes the electron from the metal. How can that do that? The nonmetal is very electronegative. Very electronegative. Using Coulomb's law, where distance is more important for force, we get the electronegativity table. Now, a couple things you want to remember. First thing, our goal is that you can look at any chemical formula and tell what type of bond it is. So there are a couple of rules. If there is a metal in the formula, the metal is written first. Metal is always written first. So you don't even have to look at the whole chemical formula. You have to identify the first element. You are not expected to know every single metal and non-metal, which is why I spent so much time laminating and taping the tables on your desk. You're supposed to use them. Do not think you're supposed to be able to glance and know. Move your lab book off your table, off your periodic table. Oh, never mind. There you go, right? Yep, there we go. Metal is written first. Remember, we learned that metals lose electrons and become cations, right? Metal is written first, lose electrons and become cations. Now, if there's a metal, it means it's ionic. And the metal is written first. So from any chemical formula, nitrogen monoxide, is this an ionic bond between nitrogen and oxygen? Find nitrogen on your periodic table right now. Is it a metal? No. So that is not an ionic bond, right? YO. Yo. Ionic bond? Yep, sure is. Ionic bond. All you have to do is look at the first one. How about KMNO4? 6H2O. Is that ionic? Sure is, because that first element is a metal. Makes that whole thing ionic. Metal's written first. The next type of bond we're going to talk about is metallic. Metallic bond. This is between, what do you think? Metals. Metallic bond is between metals. So you have a metal atom coming next to a metal atom, and they get close, and they get close, and they go like that. They get as close as they can. And then the idea is, okay, what are the electrons going to do in a metallic bond? Well, you know what they do? They just kind of whoa, 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 whoa. They just kind of flow around the metallic bond. Atom, 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 atom. The nucleus is positively charged. They come right next to each other. And the electrons basically, it's called a sea of electrons. They just swirl around all of them. So electrons flow around all nuclei. Oh, nuclei. Nucleuses? That's not right. Nuclei. Go around all nuclei. And the nuclei is positively charged. Now this makes sense because hopefully you guys know that electrons travel through metal, wires, electricity, flow. Electricity is electrons flowing around. It's called often sea of electrons. Sea of electrons. And it occurs between, you can have a pure metal, like just gold, Or you could have an alloy, a mixture of metals, like brass or steel. So you could have different pluses. This one might be a different metal. So you could have alloys, but they all act the same. And then the last type, and then I'll be done and you get to work. The last type. Anyone know what the last type of bond is that make
Covalent.
covalent? Yes. So the last type is a covalent bond. Now here it gets interesting. Two atoms come close to each other. They sum each other up. And they're like, yeah, I want your electron. The other guy goes, good luck, try to take it. So he goes, okay, I'm going to try to take it. And he's like, well, wait, no, give it back. No, wait, I want it. No, give it back. No, wait. And they literally are tossing it back and forth. Now, just like any two siblings, one atom coming next to another atom, you got the electrons. I'm going to take that electron from you and I'm going to play with it. And the other one goes, no, give it back. And he has it back. And then the other one goes, no, give it back. And he has it back. And the other one goes, no, give it back. And basically, they're sharing the electron, right? So covalent bonds traditionally are described as sharing of electrons. Sharing the electron, sharing the electron, sharing the electron. Well, this only works if they're equal sharers. Anyone have siblings?
Yep.
And is that how it works? No, it's not how it works. It's like, oh my God, that's so cool. Give it to me, give it to me, give it to me, give it to me. It's mine, it's mine, it's mine, it's mine, it's mine. Mom, you won't let me play with it. Okay, here you go, here you go. You've had it enough. Give it to me, give it to me, give it to me, give it. No, Mom. Okay, here. Now you've had it enough. Give it to me, give it to me, give it to me, give it to me, give it to me. Right? That's how it works. So there's going to be a difference in the atoms. And the stronger, the more electronegative of the atom, the one who has the greater ability to attract electrons in a bond, will have the electrons around it more often and ends up unequal sharing. Sharing can be unequal sharing. Most often it is unequal sharing. Most of the time it is unequal sharing. Unequal sharing would be what's called a polar covalent bond. Now there are a very few times, where there is equal sharing. In fact, there are 7 times where, like, twins share equally. Anyone know what I'm talking about? Twins in the periodic table. What? Diatomics, right? Equal sharing. Well, that's if they are of identical strengths. So hydrogen and hydrogen, otherwise known as H2, that bond between these two, they're sharing, and it's called a non-polar covalent bond because it is equal sharing. Non-polar covalent bond. So what else is going to do that? O2, F2, N2, Cl2, Br2, I2. Right? Equal sharing. Basically, the atoms are of equal strength because they're identical. So we get our non-polar covalent bonds. So if we go back to our worksheet, the first step for any of this is you need to be able to look at this list and straight away identify what type of bond exists between the atoms in the formula. So the first split you should do is if the first element is a metal. So, first element of metal?
No.
Nope. First element of metal?
No. Yes.
Yes.
If you're not expected to know, look it up. Don't just answer. Find it. Look, move your papers and tell me where to find it. Okay. So what does that mean? That means this is ionic. What about this guy? First element. Ionic. Oxygen? Hydrogen? Cu? So that would be ionic. C. C. First element. You're just doing first element. Sr.
Yeah.
Yep. So you're just doing first element, guys. Sn is the only element. So we don't have more than one element here. Let's skip C. Nope. Mn. So ionic. Ba.
Yep.
Find it. Everyone find Ba? Okay, ionic. Na. Yep, we did that one already. Al.
Yep.
C.
No.
C.
No.
N.
No.
Sr.
Yeah.
Sr. Yep, ionic. Brass.
Yes.
Brass. On the periodic table? Brass isn't on the periodic table. Steel isn't on the periodic table.
It's carbon.
Diamond is carbon. DNA? What the heck? Carbohydrate? What the heck is this? It's crazy count. So ionics are kind of easy to find, right? Ionics are easy to find. If it's not ionic, it's either metallic or covalent. And if it's covalent, it's either nonpolar covalent or polar covalent, right? So let's do metallics next. They're the easiest. What would be a metallic bond? It would be a metal by itself. What about this?
Yes.
Yep, metallic bond exists between multiple atoms of tin. And Au would be a metallic bond. So then that comes over to brass. Brass is not on the periodic table. It's an alloy of metals. It's nickel and copper. So that is metallic bond. Steel,
Iron and carbon.
iron and
Carbon.
iron and carbon. It's actually a metallic bond. And you might want to ask why. So your iron atoms are like this, right? I didn't draw it that great. Iron atoms are like this. And we literally force the carbon. All your electrons are flowing around it, sea of electrons. We literally force a little piece of carbon in between. It's not bound. We physically shove it into what's called the interstitial space. So these guys can't get any closer. So we literally shove carbon in there and shove carbon in there. They're not bound. We physically do that. But between the atoms is a metallic bond. But we make steel, right? Big steel plants. Diamonds we'll get to. So then the rest of these are covalent, and we need to find out, are they polar covalent or just non-polar covalent? Can we pick out the non-polar covalents right away, kind of?
Yeah.
Well, some of them we can. This guy, O2, is non-polar covalent. H2 is non-polar covalent.
Hydrogen.
Okay, so then we're left with H2O. We know it's covalent. We need to know if it's polar or non-polar. So to do that, let's just think of just two atoms involved. What is the bond between oxygen and hydrogen? So, well, how do we know? Hydrogen, 2.1, comes up to oxygen, 3.5. And what's the difference between the two? This is like a cousin, first cousin versus third cousin. What's the difference between oxygen's obviously stronger, right? How much stronger?
1.4.
1.4. There's a difference of 1.4. So that makes it a polar covalent. See, we've got a little scale here on what's called electronegativity difference. So these are covalent, but this is definitely a polar covalent bond. Now, CO2, I'm just interested in between carbon and oxygen. Carbon and oxygen. Difference 1, so is that polar?
Yeah.
Yep. Polar covalent bond. What? We'll come back to this one. We'll come back. But look at this one. We know it's covalent. It's still a carbon to an oxygen, isn't it? So that would be the same. Polar covalent bond. What about C4H10? 2.1 versus 2.5.
So
Non-polar. Non-polar covalent. Now, is there any difference between this CH and this CH? No. Just because there's more of them, we're really only interested in what happens when a carbon meets a hydrogen. And that happens single atom to single atom. So this is going to be non-polar covalent. NO. It is polar. It's just the tiniest bit polar, right? It's just barely polar. So it's okay to be like weakly polar, but technically it is a polar covalent bond. Yes, polar covalent bond. Diamond is a carbon to carbon to carbon bond. Carbon, carbon, carbon. Right? It's just a bunch of carbons bound together in a structure. So if you is there a difference, an electronegativity difference between a carbon and a carbon? No. So these are non-polar covalent bonds. DNA and carbohydrates. DNA and carbohydrates. These are big molecules, right? Big molecules. Stay with me on that. Stay with me on that. And then we have this guy over here. Anyone know what this is called? Glucose. And do you remember the structure of glucose?
C6H12.
Okay. Well, the structure, I don't know. Did you draw it like this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then like this.
I think I saw a drawing of that, but I never personally.
Right. And then what is it? What we got? We got a OH, H, H, OH, H, OH, 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 and 6, OH. Right. So like this is imaginary in books. Because as soon as you put that in water, it's going to chain up. It actually creates a circle. At every point on the circle is a carbon. You got an oxygen. So here's a carbon, 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 and here is a CH2OH, right? So CH2 is actually C with your H2 and then to an O and to an H, right? So this is attached. So here's my H and here's my H, and this carbon is going to right there, this carbon, which is right there. So that's just what CH2OH looks like spread out. CH2OH spread out. This carbon is right there. You'll often see them abbreviated. And then what you get at these points, there's a carbon, and carbon is tetravalent, you're going to have an OH and an H. Oh wait, those are H's. And then an OH and an H and an OH and an H. 1, 2, 3, 4, 5, and then an OH and an H. 6. C6 H12O6, right? That's HAM. Electronegativity difference. What are the possible bonded atoms? Carbon to hydrogen. Is that polar?
Yeah. I mean, no.
0.4, right? But then there's also carbon to carbon, nonpolar. There's also carbon to oxygen.
Okay.
That's polar. That's polar. And there's oxygen to hydrogen. This one's polar, right? Polar covalent, non-polar covalent, non-polar covalent. So within a molecule, you can have multiple types of bonds, and that's okay. That's okay. So I know the table says one thing, but you're gonna have multiple answers as life gets more complicated. Life has changed, and your change is it's not always going to be just one answer. How did I lose the worksheet? I'm sitting right here. I didn't get up. Where is it? Oh. So here, you would just write, you have polar covalent and non-polar covalent, right? You have both, polar covalent and non-polar covalent. This is a carbohydrate. Carbon and your hydrogen, 8 carbon, hydrogen, oxygen, carbohydrate. This is a carbohydrate. So the same DNA would be polar covalent and non-polar covalent. So they contain both. But what they don't contain is ionic. Right? They don't contain ionic or metallic. So that, I think, is a very good start for you to finish this page. Ooh, crap. Pepper dissociation. Okay, super quick. Ionics have a metal and they dissociate. On the periodic table, find Ba on the one on your desk. What charge does it show? +2. So when this dissolves in water, you get Ba +2. Now find oxygen. Right? Oxygen -2. Basically, it splits apart into its charged ions. And how do you know what the charged ions are? You look on the periodic table. Then the only other thing is to use AQ. AQ. AQ stands for, and it's a Q, guys. It's not a G. AQUEOUS. Aqueous. Didn't you learn this in bio? Life is in an aqueous environment, right? Aqueous means dissolved in water. How did you go through biology and not learn aqueous? All of the biological things happen in a water environment. You learned osmosis.
Yeah.
Right? So that's aqueous solutions, or what osmotic pressure is from aqueous solutions. So living things, all the chemistry that occurs in a living thing with a metabolism occurs in aqueous solutions. So keep that separate from whether it's a solid, a liquid, or a gas, right? You can have solid iron. You can heat it up enough to have molten iron in liquid form, and you can vaporize it so bad that it turns gaseous. But iron is not going to be aqueous unless it's dissolved in water, right? So liquid is not the same as aqueous. Aqueous is a solution. And that's what you're describing here. You're putting a salt into water, a solution. And then it's just asking you to balance it. If I have one barium here and I have one here, I'm good to go. I have one oxygen, I have one oxygen. Good to go. Yes?
What about the elements that have like multiple ions?
Okay, like AlCl3. So aluminum, you look on the periodic table, it's +3. And then you looked for chlorine. What was chlorine? -1. And they are now aqueous. And then you say balancing for the end. There's one aluminum here and one here. We're good to go. How many chlorines? 3. So how many chlorine ions? 3. 3 chlorine ions. Let's think about what it looks like. You have an aluminum, and it's attached to a chlorine, and a chlorine, right? When that goes into solution, it splits apart. So we have an Al with a +3, a chlorine with a -1, a chlorine with a -1, and a chlorine with a -1, right? So what water does is it literally pulls this apart. It pulls it apart. And when it pulls it apart, you get 3 chloride ions and 1 aluminum ion, right? Water is pulling it apart. And what you know of water, the hydrogen ends are going to be attracted to the chloride ions, right? Doesn't that make sense? Coulombic forces, opposite attracts. And remember, water is H2O. So we have here are your water molecules. And you could probably fit a bunch of, there is a limit to how many you can fit around there. But what end would be attracted to the aluminum? Yep, the oxygen end. So here you would draw the oxygen with your hydrogens over here. And then you can fit a bunch more of your water molecules. I know they look like Mickey Mouse heads. Right? So water literally pulls this guy apart, surrounds it. And it's because it's polar. It has charged in. Okay, so get to work, see if you can finish this. I think you can.